student, postdoctoral fellow at Nagoya University in Japan. In this presentation, I will mainly talk about my PhD work that I did at the Laboratoire d'Astrophysique de Bordeaux with Hervé Bouy and Emmanuel Bertin. And my PhD title is the same title than this seminar, Robust Detection of Astronomical Sources Using Convolutional Neural Networks. So in my PhD, so we were interested in source detection, mainly in wide field optical and near infrared images. So source detection consists of detecting all the sources that can be stars or galaxies in images, like we can see in those examples of sextractor detections in the Canada-France-Hawaii Telescope Lensing Survey. And so source catalogs are at the basis of many astrophysical research, and most astronomers don't work with images but work with catalogs directly. And due to the large amount of data that we have now, we have automatic source detection method to perform source detection, but those techniques are limited. We can see, for example, here near this bright star, we don't detect some small sources, or we can have problems to deblend sources to separate close sources or sources that can overlap. And so my PhD aim was to improve those source detection methods. And a big aspect of my PhD was also to tackle contaminants in images, because astronomical images can be contaminated by various defaults that can trigger false detection, and that can be an important source of noise in the output catalogs. For example, here we have the detection of the SDSS in yellow and pan stars in red, and we can see some false detections on diffraction spikes of the bright star, or for example, false detection on a satellite trail crossing the image. So one big part of my PhD was also to perform robust detection regarding contaminants. So I will first describe a bit the context, more specific context of my PhD, and we will see after that the current source detection solutions, their limitation, and we will go to convolutional neural networks that we want to use to perform source detection here. And then I will describe the two main tools I have developed during my PhD, which is a contaminant identifier first, and then the source detector prototype that we have done. So a bit of context first. So my PhD work lied within two main projects. So the first project is Cosmic Dance, which is a project led by Hervé Bouy, one of my PhD advisors. And the aim of this project is to unravel the origin of the initial mass function of stars. So the mass function is the function describing the number of objects with respect to the mass of those objects, as shown in this figure. And so to study this mass function, we study stellar clusters because members of those clusters share some initial birth, and then can give some clue about the mass function. But to study those clusters, we need to identify the member of those clusters, which consists of isolating a few sources among the millions of sources that we can see in the images. One way to identify those objects is to use proper motions that are the apparent motion of sources on the sky. And we can see here on those on those right ascension and declination diagrams that, for example, we can isolate members of the Pleiades here because they share some proper motion compared to the stars of the field. And so to do that, we need to detect and measure the position of millions of sources precisely. So we need a precise source detection software. And as one aim of cosmic dance is to use the maximum of archives that are available. So in order to go to fainter magnitudes and to detect also the faintest parts of the IMF. And so as we use the maximum of archives, we also need to have a robust source detection software that can apply to various images coming from different instruments and that can have different image quality. The second project is Euclid, and is more related to the CNES. And so the aim of Euclid is to probe dark matter, dark energy, and the expanding universe, and to constrain cosmological parameters. And so to do that, we need a precise census of galaxies and galaxy clusters, and to make galaxy shape measurement. And so to do that, we also need a robust source detection software. And we also want galaxy magnitude measurements, and to have those measurements to compute redshift, the Euclid photometric coverage is insufficient. So there is a need for a complementary ground-based data. And so in the scope of Euclid as well, we need to process a huge data volume and with heterogeneous space-based and ground-based images. So this ground-based segment is 50% of the consortium resources, so it is not negligible. And so to process all this data, we also need for robust and generic source detection software. And this PhD work is also of interest for Source Extractor++, which is the next version of Sextractor that is developed in C++. And that follows the same spirit of Sextractors that also seek for robust and generic source detection. And Source Extractor++ is also partly developed for Euclid and by Euclid member collaboration led by Pierre Dubat at Geneva University. So now that we know that we need source detection, a robust source detection software, we can see how source detection is performed now. And in practice, current source detection pipelines proceed in several steps. One of the first step is to estimate the sky background and to subtract it, which is essential to detect the faintest objects. And this sky background subtraction, this sky background estimation is generally made locally by estimating, for example, the mode of the image histogram. And then the core of the detection is the match filter that I will describe a bit in more detail just after. And that aim is to enhance the presence of sources in the image. And after the source enhancement, there are two methods to detect sources, rightly speaking, which are peak search, which consists of finding the local maxima in the image, or thresholding, which consists of retaining only the pixels that are above some value. And once we have detected objects, it can happen that we detect multiple objects as a single object. So we apply deblending procedures, like, for example, multi-thresholding in Sextractor. And by thresholding at different level, you can separate multiple objects. So here we have the whole example of Sextractor processing. So as I said, the core of the source detection is a match filter, which consists of correlating the input signal, with some pattern, some template. And it is known as the optimal linear filter to maximize the signal-to-noise ratio of a given isolated pattern in the presence of stationary noise. And in practice, it will be a convolution with the PSF if we want to detect, because we will want to detect PSF-like objects. And the problem is that it still has some limitations because the noise must be stationary and the patterns that we are seeking for must be isolated, and it can work only for a pattern at a time. So in practice, it will be limited because, for example, sources can exhibit various scales and shapes. So the fact that it can only detect one pattern at a time will be limiting. We can see, for example, here on the right, we cannot detect the low surface brightness galaxy because it will need a specific match filter pattern to be detected. And another problem is that source can overlap or blend, and the match filter is optimal only to detect isolated patterns. And so here we can see on the left two different strategies when we have a very bright source. For example, so the SDSS is really conservative and it will not go too much in this area and try to sacrifice completeness for contamination. And in the contrary, Pan-STARRS is trying to go in this area and will have more contamination and at the price of a better completeness. And so our approach in my PhD was to extend these methods with supervised machine learning and in particular convolutional neural network to perform more adaptive filtering and segmentation, and also a nonlinear segmentation. And so this techniques has been shown to be very efficient in various computer vision tasks, and it also enables to learn directly from pixel. And so now we will a bit change our framework. Instead of having more algorithmical approach, we are now in a supervised learning framework, which is depicted here, and which consists of learning from an input-output data set that we have available. And to learn, we will iterate learning steps with a model. So the model is made of our neural network parameters. And thanks to these parameters, we will make a prediction. And as we know the theoretical output that we should obtain, we can compute the prediction error with a loss function. And based on this loss function error and on an optimization method, we will optimize all the neural network parameters, often with a method based on gradient descent, to make better prediction in the future. So learning will consist of iterating a lot of learning steps like this on our data set. And even if these methods need a lot of data, this is something that we have in astronomy because we have huge amounts of data that are available in various archives, or we can also simulate a lot of data. So before talking about my work in more details, I will describe a bit more convolutional neural networks. So as stated in their name, convolutional neural networks use the convolution operation, which is efficient to process grid-like data. and which consists, which can be viewed as a convolutional kernel that we shift through the input image, and we will, at its position, we will compute the output value of the given pixel by computing the weighted sum of the kernel values with the input image. And so the convolution will enable to capture features with translation equivariance, which means that the same feature at a different location in the input image will be detected at the same location in the output feature maps. And so here we have an example of convolution that can, for example, detect edges in an image. And in the convolutional neural network, we will learn the convolutional kernels. And so we will learn from data which features are relevant for the tasks that we need to solve. So inside the convolutional neural network, we'll have convolutional layers, which are made of three different elements. So the first one is the convolution that I just described. So we will compute different convolution with various filters of the input image, giving us several feature maps. And then we will introduce a nonlinear behavior with an activation function, which is that is pointwise applied to the feature maps. And one famous activation function is a rectified linear unit, which is linear on the positive input values and that is not active on the negative input values. And finally, we will apply a pooling operation, which have several aims. So one of these aim is to reduce the dimension of the feature maps inside the network, because as we will see just after, we will stack convolutional layers in the network. And so this enables to reduce the computational burden of the network. And this pooling operation also enables to make feature selection. So here is an example of the most commonly used max pooling operation, which is max pooling, and which consists of taking the maximum value of here 2x2 tiles of the feature map. And this max pooling operation will also introduce a small translation invariance property in the network. And more importantly, we'll give a hierarchical view for the network. As I said, we stack convolutional layers in a network. So thanks to the pooling operation, the next convolution in the network will have access to a more extended context from the input image. And stacking convolutional layers will enable to combine the features that we detect through the network and learn more and more abstract data representation. And this data representation will be given to fully connected layers where, unlike convolutions, we will have parameters connected to all the input features. And we will combine these features to output, for example, probability scores to belong to some classes or whatever. So here we can see the main property of convolutional neural network to learn representations of the data. So this is a convolutional neural network that has been trained to classify galaxies. We can see here on the top left example of the first layer convolutional kernels, and we can see on the top right image an input image with the first feature maps in the network and the pooled feature maps here, and then the subsequent feature maps and pooled feature maps in the network. And we can see that it learns more and more abstract representation, and this representation is given to the fully connected layers that can classify the input image. And on the last image here below, we can see on each row, we can see inputs that maximize the same fully connected network neurons. And so we see that there are groups of neurons in the fully connected layer that specialize to gather some feature. For example, here to the spiral galaxies, or here to the edge-on galaxies. And in our scope of source detection, we need source segmentation maps. And so we don't want to classify images, but we want to classify pixel, which is the definition of semantic segmentation. And so we will modify a bit our convolutional neural networks. So here is a convolutional neural network for semantic segmentation, and it starts with the same structures that we have seen, with convolutional and pooling layers that are stacked, and we learn a representation of the data. But instead of giving this feature to fully connected layers to associate one label to the whole image, we will use upsampling layers to re-upsample the feature maps to higher spatial resolutions until we get to the initial spatial resolution of the image to make a prediction at the pixel level instead of at the image level. So one way to upsample the feature maps is, for example, the unpooling operations, which consists of remembering the indices that we have used during the pooling operation in the first part of the network to re-upsample by putting the pooled value at the corresponding places in the image in the unpooled feature map. And so doing so, we can retrieve the initial spatial resolution and make prediction at pixel level. And so now I will talk about the first part of my PhD work, which we devoted to the contaminant identification. So in the literature, there are not a lot of approaches that does all-in-one contaminant identification like we aim to. And so current method either focus on a single contaminant, like Van de Koom et al., which developed LA Cosmic, which is a software to detect cosmic rays in images. And other methods rely on a priori instrument knowledge, like for example, the HAC pipeline. But they cannot apply to a wide variety of images like we want to do. And so our approach has been to develop a CNN, a convolutional neural network, to detect all contaminants at once. So we classify contaminants in two different groups, local contaminants and global contaminants. So local contaminants are the contaminants that affect the image at the pixel level. So we identify them with semantic segmentation, as I just described, while global contaminants affect the image at the image level. So they need to be dealt with image classification. And so in the following of this presentation, I'll focus only on local contaminants that we tackle with Maxime. So here is a table describing in green the contaminants that are currently included in Maxime. So to illustrate a bit those contaminants, so local contaminants can come from different sources. We can have electronic contaminants like hot pixels or dead pixels, which are pixels that have abnormally high or low values. We have pixels that can saturate, especially with bright stars, and also persistence effect, where a bright star can leave a remnant pattern in the consecutive exposures. We can have contaminants coming from optical sources, So for example, with residual fringing patterns, the diffraction spikes of stars, and reflection and refraction that can occur in the telescope, and that are very common now in wide field cameras, which uses a lot of correcting optics. And finally, we have also contaminants coming from external events, like cosmic rays, which can be worm-like here or more punctual, depending on their incidence angle with the detector. And satellite trails, for example here, or nebulosities, which are a bit particular case because nebulosities are also astrophysical objects, but we consider them as contaminants because they can disturb the source detection or measurement process, and so we need to identify them. So to identify those contaminants, we developed a convolutional neural network for semantic segmentation, like I described before. So it uses the same main structure with convolutional and pooling layers in the first part, and unpooling and convolutional layers in the second part. It just has one more specificity, that we extract predictions from each resolution in the network to use the maximum of information we have in the network. So we have 5 different predictions that we combine to make a final prediction. And in the end, Maximask outputs one output map per contaminant, telling for each pixel the probability that this pixel is affected by the given contaminant. And we use as output a sigmoid activation function to enable non-mutually exclusive classification. So a pixel can belong to several classes at the same time. For example, it is useful to classify a cosmic ray, which would be in a nebulosity pattern, as both cosmic rays and nebulosity. And to train our network, we built an input-output dataset by ourselves. And to do so, we identified the cleanest images in the Cosmic Dance survey, which is a survey of my PhD advisor, Hervé. And we extracted clean images, so uncontaminated images from it. And we found we found images, clean images in 3 different instruments. The dark energy camera here on the left, the mega camera of CFHT in the middle, and the HIC camera here on the right. So given those clean images, we add contaminants by ourselves in those clean images, so that we know perfectly for each contaminant which pixels are affected by this contaminant. And we can build the ground truth. So here is the ground truth for this image, where all the contaminants are represented in a single color image, where each contaminant is assigned a color. But in reality, we have one mask per contaminant. One mask for contaminant to train the network. And here we can see, for example, in red, cosmic rays, or in orange, satellite trail, and etc. So we generate a lot of contaminants, a lot of images, like training samples like this to train our network. And when training, one important problem that we faced is the class imbalance. That is an obstacle to correct training, because, for example, for cosmic rays, we have much more pixels that are non-cosmic rays compared to pixels that are cosmic rays. And so statistically, the network can be biased to predict that all pixels are not non-cosmic rays, because you would have a really high accuracy with doing such a prediction. And so to circumvent this problem, we used a weighted symmetric cross entropy as loss function. So the original cross entropy would be without this weight. So we just take the logarithm of the prediction of pixel P of class C if it belongs to class C, or the logarithm of 1 minus this prediction if it does not belong to class C. But here we also give a weight to each pixel depending on the class proportion it belongs to compensate for the class imbalance in the training set. So we train Maximask with 50,000 images of 400 by 400 for 30 epochs, meaning that the network have seen 30 times the whole training set. We use the Adam optimizer and TensorFlow with a GPU backend, and it takes approximately 1 day to train. And here is an example of input image with the corresponding feature maps of the first layer of the network. So we can see different features it detects on the first layer. After training, we can first inspect some qualitative test set results. So these are here test images. That means that these are images that have not been used during training. And this is the ground truth we have, as these are still simulated images. And these are the prediction here on the right. So we can see that apparently the training procedure was good. But we also make quantitative performance measures to assess the performance of the classifier. So we use some common measures of true positive rate and false positive rate. So the true positive rate is the ratio of the true positive to the number of positive samples, positive pixels to belong to one class. And the false positive rate is the ratio of false positive to the negative sample. And so we make the traditional ROC curve, where we represent the true positive rate with respect to the false positive rate for a different detection threshold. So we can compute the true positive rate and the false positive rate at different threshold between 0 and 1, because the network outputs probabilities. And each threshold of detection gives us 1 point in the ROC curve. And one point to mention is that even if these are ratios that are robust to class imbalance, we still represent the false positive rate in a logarithm scale here, because the true positive rate is indexed on positive samples. So if we remember the case of cosmic rays, we have a very small number of cosmic rays pixels. So P is very small, while N is really large. We have a large number of non-cosmic ray pixels. So a really small change in false positive rate will affect a lot of pixels in practice. So we are seeking for very low false positive rates, and that's why we show a logarithm scale here. But if we want to, we may want to avoid this logarithm scale, and to do so, we can use another measure, which is purity, which is the fraction of true positives among the predicted positives. And here we represent a similar curve, so at different threshold, the true positive rate versus the purity. So we can do this for every class in the network. For cosmic rays and trails, we verify that the network performance is a bit better on the instances of cosmic rays or trails that are brighter. So by retaining only those that are greater than 3 sigma of the sky background. And we make, for cosmic rays, we make a comparison with LA Cosmic, where in 2 different regimes with well-sampled images and undersampled images. And we can see that in both cases, the CNN can give a better performance because it is more on the top left of the curve. It has more true positive rate and less false positive rate than the 2 points here that represent the LA Cosmic performance. Finally, one point that we also develop is the fact that given a perfect training, that is a training without underfitting or overfitting, and given that we are our training data has the same likelihood than the data we will apply our network, we can say that we can interpret the output probabilities of the network as Bayesian posteriors. And doing so, we can adapt the prior, which is the expected class proportion in data that we have, because one point that we can mention is that our, in terms of class proportions, our training data are unrealistic. We don't have that much satellite rays in images or that much cosmic rays in images. And so we want to target new class proportions when we will use maximize for inference. So thanks to this Bayesian posterior interpretation, we can do this, and we can modify the priors of the probabilities of the network. So here is the formula, but it is not really intuitive, but what we can simply view it as dividing by the training priors and multiplying by the expected priors that we want to target for real data. And so by doing so and normalizing the probabilities, you can have this formula. And to see a bit clearer what it does on the probabilities, here is a little plot where I represent the modified probabilities with respect to the raw probabilities, where raw probabilities have a prior of 0.5. So we expect 50% of positive samples in our data and 50% of negative samples. And so we can see the effects of the prior modification and the probability for different target priors here. And so in the end, the transformation is strictly monotone, so it will not change the global performance of the classifier. And as we can see here, with the same work curve with different probabilities, we get the same work curve. But what the Bayesian prior modification does is simply to shift the probabilities along the work curve. So here is, for example, the raw work curve with some of the detection threshold that are displayed. And if we target a lower prior, we will shift all the probabilities of the network on this side of the work curve, while we will shift them on the other side when we target a higher prior. So in the end, it will enable to maybe target different behavior of the classifier. And to verify that this Bayesian prior modification is correct, we can check for calibration curves where we represent the fraction of samples, of positive samples, with respect to the probabilities of being positive. And for example, here I represent for cosmic rays the raw posteriors in orange and the modified posteriors in green. And we can see that after the Bayesian prior modification, we can indeed have better calibrated probabilities, because we expect to have the same, if we take the mean of the posteriors, we expect to have to have as value the fraction of positive samples. So this has been done. When I say raw posteriors, these are the raw posteriors after training. So what we should have in mind is that these probabilities have the influence of the class proportion in the training set, and also the influence of the weighting that we did in the loss function. And we see that with our Bayesian prior modification, we can compensate from those influences and have well-calibrated probabilities on a target testing set. And we can make the same calibration curve for each class. And we can see that for example, nebulosities and trails, it seemed to work. It seemed to be less efficient. One reason to that may be that that for these classes, which are more extended, the class proportion is less well defined. It's difficult for the network to match the exact behavior that we built by building the ground truth of those classes. So we also use our classifier on real data. So here is an example of inference results on an image from the dark energy camera, where we can detect the satellite trail or the cosmic rays, the diffraction spikes here. So, and we also test if we can detect the Starlink satellite, which will be more and more numerous in the sky, and more annoying, especially for wide field survey, as we can see here, because these are a constellation of satellites that covers the whole field of view. And with Maximat, we can identify those satellite trace images. We also test Maximask on data, on a type of data that has not been seen during training and not been used during training. So these are HST data with the input image here, the prediction of Maximask, and the image cleaned by the HST pipeline on the right. So we can see, for example, that we are satisfied that Maximask can make the difference between some small undersampled stars and cosmic rays, even if it is a type of data that does not used during training. And we also tested Maximask on some Euclid simulated images, where here we have the Euclid simulated ground truth and simulated image, and here a prediction of Maximask, where as we have the ground truth thanks to simulations, we can even compute a rod curve to assess performance quantitatively. And I also show that we can train, if we train a network separately on the Euclid data, we can have a really even a higher and better performance. So here are the rod curve of cosmic rays and ghosts, which are included in the Euclid simulations, with the ground truth, an input image, and an example of prediction of a network trained specifically on Euclid data. So now that we have seen how we can tackle contaminants, I will talk about our source detector prototype. So as I recall, source detection challenges are that sources can exhibit various scales and shapes, and sources can overlap or blend. Also, images can be contaminated, but we've just seen this point. And one major difference between the contaminant identification and the source identification is that the source detector must be instance aware, which means that it must detect each object individually. So here is, for example, an input image where, and here in the middle is what would do a semantic segmentation network that is classifying object versus non-object, and this is what does Maximask. But for source detection, what we would need is instance-aware segmentation, where here the network is aware that those green pixels belong to objects, but a different object than those blue pixels or yellow pixels. And the problem is that this involves a lot of difficulties to design architectures and loss function, especially when we want to tackle deblending and non-mutually exclusive segmentation. And one of the most famous approaches to perform instance-aware semantic segmentation is mask or CNN, and it processes in two different steps. First, there is a CNN that predicts what are called region of interests. So it predicts a lot of potential object locations in the form of bounding boxes, and it uses a procedure to refine all these predictions to only some objects. And then there is a second network that takes as input those rescaled bounding boxes, and that performs segmentation and classification on each rescaled bounding box. And so we decide to not apply directly this kind of methods to source detection, because we found that boxes are not really well suited for sources, which are objects that doesn't have real boundaries, well-defined boundaries. And also the rescaling of each bounding box is implying interpolations, and we can see that the masks and the output masks are not perfectly delineating objects. And also this is a method that has some difficulties to tackle the blending. And in fact, there are not a lot of methods tackling the blending because in images of natural scene, this is not really a problem of deblending that we have, but more a problem of occlusion. That is that an object is in front of another, but is hiding another. But as objects are opaque, we don't. It's not really the same problem as deblending, where we have in each pixel the contribution of several objects. And so instead, we decide to rely on semantic segmentation, and our CNN prototype for source detection is a multi-scale, is doing a multi-scale footprint segmentation. So we have as input an image, and as output we have different maps where each map corresponds to a given scale, and so sources are identified in one of those scale maps, and each source is identified in one given map by its footprint. So with our method, we need to define footprints for each source, and we need to define a scale affectation for each source as well. So to define source footprints, we identify two main definitions, which are the first one is to take the brightest pixels forming some fraction of the total source flux. So we have those footprints at different fraction of the total source flux represented in the middle image here. And another definition would be to take the pixels that are above some fraction of the maximum intensity of the source, and we have source footprints at different fraction of the maximum intensity of the source here. So you can see that we obtain more or less the same footprints, but in fact the most critical part in the definition of the footprint is to set the fractions here and to have a compromise between small and large footprints, because having small footprints will enable to deblend more sources within the same scale, because we will be able to separate eventually two overlapping footprints. But also having too small footprints will lead to maybe some class imbalance issues that we would like to avoid if possible. So we have a compromise to do between small and large footprints. And we finally end with the choice of the first definition with taking the brightest pixels of sources that makes 1/4 of the total flux of the source, which are represented by the yellow footprints here. But this is something that can change depending on the data we have. As a scale affectation, for now we have an arbitrary scheme where we have a maximal size of footprints for the first scale, and then we multiply this limit by 4 for the subsequent scales, because one object that is 2 times bigger in an image will have 4 times more pixels in the image. And so we define 3 different scales given our current data. And so how do we do to have such images with their ground truth? We rely on noise-free images of isolated sources so that we can compute only ground truth on those flux, on these noise-free flux images of isolated sources. And we can build whole images from scratch by putting these sources at different locations and building images. So for stars, we rely on SkyMaker, which is a astronomical image simulation software, where we can see here different star profiles. And for galaxy, we rely on cosmological simulations, and we use the images from 3 different cosmological simulation projects. Here on the left, we have galaxies that we use from Horizon IGN project, which has been rendered by Clotilde at IAP. And in the middle, these are galaxies that we took from the Illustris 3NG cosmological simulations. And on the right, on the Vela cosmological simulations. So starting from those images, we build, so we start from, as I said, isolated images of sources. And so we can compute their footprints on those isolated images, and then we can add them at different locations in an image and generate a sky background, adding the noise characteristics of astronomical images, and eventually adding contaminant, like shown here. And starting from those isolated sources, we can have the ground truth and the footprint maps to train our network. And so this is some example of results after training. So here we can see on the top row detection made by Sextractor and the ground truth footprints of this image and the prediction of the network after training. And so we can see, for example, one benefit of the multi-scale approach, where here, well, the source is a bit detected, but we can detect it better with CNN. And for example, well, it's here, the prediction, sorry. And we can also detect the source here that is not detected by Sextractor near this bright source. And we can see also on the bottom row example, one advantage of the CNN is that it is naturally robust to the presence of contaminants in the image, where we can see that with Sextractor, it's making a lot of false detections on the trail or on the hot column here. But this is not the case of the CNN. And then we perform some quantitative measures as well. And we use the completeness and the contamination. so we compute those values at different threshold of detection. So we use a threshold at some sigma above the sky background for size tractor. And as a threshold, we use different threshold between 0 and 1 for the probabilities of the CNN. And we compare performance here in two different regimes. So on the left, we can see completeness versus contamination graph with images that can be contaminated, and on the right with uncontaminated images. So we can see, especially for the contaminated case, that we can reach better completeness at a given contamination rate, with the CNN. And so finally, we also apply the CNN to the images I shown at the very beginning of my presentation, and we can see that the CNN is able to detect sources close to the very bright source here, for example, or close to this one, which was not possible with a size tractor, and that we can deblend more sources, especially, for example, if we look at this area or this area, here we can accurately detect the sources and deblend them. So as a conclusion, so we have seen that current source detection limitations can be overcome with convolutional neural networks, and that we have seen in the first part that Maxime can identify various contaminants in images, and that we have built a custom training set that we can tackle class imbalance with a weighting scheme in the loss function. And we can have a Bayesian probabilistic interpretation of the outputs to adapt the probabilities to different contexts in real life. And so Maximax has been published at ANA and is available on GitHub for inference for now. And it has already been used a lot for the cosmic dance survey. And then in the second part, we have seen that we can perform source detection with convolutional neural networks and reach better than state-of-the-art source detection. With our network, we can naturally manage multiple source scales so that objects that have different scales can be naturally deblended. And we have seen that the CNN can have a natural robustness toward the contaminants. And we have an article in preparation about this work. As a perspective, for the contaminant identifications, we could improve the identification of some defaults, especially diffraction spikes, which are the less well detected contaminants as of now. And we aim to include other contaminants that are not included yet, like especially infrared features like crosstalks or the or saturation patterns that are not the same as in optical cameras. And also a very problematic contaminant are all the contaminants that appear as reflections or scattered light in a telescope, like I show here with HEC examples that we also want to tackle in the future. Also, another aspect that we consider would be to extend Maximas to in-painting, that is to replace the contaminated area to clean the images. And for the source detection, we have still a prototype, so these are still some preliminary results. So we should still work on the training set, which is linked to the also optimization of the footprint definition and scale affectation. And on the training set perspective, we need to include more extended objects and have a more realistic object distribution in our training images. That may require to work with galaxy population specialists. And still, we have the implementation of this detector is ongoing in source extractor++. And another perspective would be to extend such a detector to multi-channel images or to apply it to a specific instrument. And one important point as well is to study the detector selection function to make a real astrophysical studies afterwards with the catalogs of the CNN, because it will, as it is an adaptative method, it will have a more complex selection function than traditional algorithms. So thank you for your attention. I'm ready for question.
Thank you, Maxime, for this very interesting presentation. So we'll take a few questions. We have one from Françoise.
Yes, in fact, it was very interesting. I just naive question that when we do the cosmic ray identification or any external perturbation, we have several images, and of course the perturbation is only on one image out of 10. So do you use also this fact that it is easy to recognize this external perturbation by having several images of the same field of view?
Yeah, it's true that some pipelines, for example, the LSST, a lot of image analysis will be based on the fact that they will have multiple exposure of the same areas of the sky. And yes, image differencing can be a good way to identify the contaminants that appear just at some time, like cosmic rays or satellite rays, for example. But in our work, we wanted to make the most generic possible algorithm, so we don't use multiple exposure of the same areas.
Okay, thank you.
So is there other questions? Yes, we have two, Philippe and Rodrigo. Go on, Philippe.
Well, as you said, you showed the effect of the imbalance for the for the cosmic rays or for the artifact in the images, and at the very end you mentioned the fact that it's probably the same problem for source identification, in particular for galaxies. If you don't show the same population, I suppose that you will have some imbalance problem, and you may not find properly a given type or family of objects. So my question is, do you already classify the objects? I mean, or do you need to plug a classifier to identify elliptical, to differentiate elliptical or spiral galaxies, for instance? I suppose this is doable.
So for now, the detection, the CNN is just performing detection and not classification of the sources. So yes, we would need an additional, what we could do, for example, is to have another CNN that would take centered stamps on the detected footprint, and that would classify each source, for example. But currently, we don't classify sources.
Because if you want to test if the distribution is correct, I think at some point you will need to know what kind of galaxy or what kind of, I mean, to type in some
maybe with objects. Maybe even without classification, we could do that with because we could have the ground truth of the galaxy type we put at each location, and afterwards we could check for each population of galaxy, for example, which how well we detect them. So if we know in advance which type of galaxy we had at which location, we could study such bias.
Well, in a way, you're not so far from classification by doing so.
Yeah.
Okay, thank you.
So So we had another question from Rodrigo.
Yeah, hi Maxime. That was really, really interesting. I enjoyed your talk very much. I was just wondering, have you tried to see with your source detection software what happens when you look at very simple systems such as well, situations like where you're just trying to detect point sources that may be crowded? Is there any possibility to actually improve the detection, the current detection algorithms in that situation?
Yeah, it's true that in this presentation I showed mainly results on galaxy fields, but we also have crowded stellar fields in training imaging, so it can also do some good work in these fields. Well, for now, the main limitation of the approach is that if two source footprints overlap within the same scale, we cannot deblend the sources. But as long as they don't, we can separate objects.
So in that case, so you can't deblend two point sources in that case. So I suppose it kind of means it wouldn't be usable for like globular clusters or such.
We shall see. At some point, we try to include some images in at a confusion noise regime, but maybe we should. We did not explore that much yet, but yeah, that would be maybe a good perspective as well.
Well, thank you very much. In any case, really interesting. Well done.
So, is there any other questions from the participants? Waiting a few seconds for someone to raise his hand. So I will ask a few ones in the meantime. So I had first a question about your perspectives, because you said you were interested in multi-channel images. So I was wondering if you had preliminary results on that, or at least thoughts about what you expect to be the difficulty of such task when you add multi-channel inputs.
Yeah, no, we have not really started tackling this point. So I know it's true that on the simulation, it would be complicated on the simulation to simulate multi-channel images, I guess.
Mm-hmm.
So, well, as usual, I think that the main problem will be the data. And, yeah.
Okay, so if you haven't not much thought about it, it's okay. So I have a more technical question about the fact that you are doing pixel segmentation. So have you tried to do segmentation in another way? So you showed, for example, the boxes from fast RCNN networks, but I don't know, have you thought about using ellipses, or I don't know, some parametric representation of a source rather than using the pixels, because in such a case you could have easier overlaps between your sources.
Yeah, that's true. That for now we didn't explore that much, like doing something similar than mask RCNN with maybe ellipses instead of bounded boxes, for example. This would may be wise, but we didn't explore that yet. So yeah, that should be nice to do it, to compare how different the prediction could be.
Yeah, that would be very, very interesting, I think. So that's all for my questions. So if nobody has more questions, wait a few seconds, but I think we can stop there. I don't see any more questions. So thank you again, Maxime. It was very interesting, very nice work. So I thank all the participants as well, and we will see you next week for the next seminar. Thank you very much.
Thank you.
And Maxime, if you want to stay a bit, we can discuss a bit more. En français, si tu préfères.
Si vous voulez. Oui. Comme vous voulez, si vous avez plus de questions, c'est quoi?